All right, great. Um, all right, well, so this is module 2, and we're going to talk about soil erosion and sediment transport. So the process of erosion occurs in two phases. The first phase is detachment. So this is when the individual particles of soil get dislodged from the soil itself. And lots of things can do this. Mostly we're talking about rain droplets. Running water, of course, can erode soil, and in some parts of the world, wind's a big deal, where there's little rain and lots of wind. So we don't have that much of a wind problem in North Carolina, but we do have a real problem with rain droplets dislodging particles. And I'm going to start reminding you here about thinking about, well, how can I make that not happen? And so hopefully most of you are thinking, well, if you cover up the soil, then you're not going to get that kind of detachment. All right, and then the second part of erosion is transport, moving those particles in water across the landscape and hopefully into a sediment control device that we've set up. But these are the two phases, and that's sort of what you should be always thinking about when we're putting out best management practices, whether it's ground covers or sediment control devices. So here's that detachment you can see in this picture. As the soil becomes saturated, when the raindrops hit that soil, it can splash those particles pretty far. It's surprising how far those can go. So that's erosion in itself without even having any water moving. And so you get those little craters and the soil gets splashed from side to side. And again, picture this same scenario, but covered up with straw. So you wouldn't have any of this happening. And if we're on a slope, then those particles tend to get splashed further downhill. And in this case, we can actually have erosion without having water moving. So in other words, the droplets are splashing the soil further down the slope than they are splashing it up the slope. And so you have a net amount of erosion going down that slope. And then we have that transport phase. You can see in the lower left, that's a lot of transport, a lot of sediment being moved by water that was probably detached by real erosion and raindrops all combined. And unfortunately, what can happen then is we end up with a lot of sediment, uh, hopefully not off the site, but on the right, that's sediment in a stream and a wetland. So that's really why we're here today, is to avoid that from happening. So once the soil becomes saturated and cannot accept any more water from the sky, then we start to have water flowing across the soil. Now we have a lot of different types of soil in North Carolina. They're usually some kind of a mix of sand, clay, and silt, which are the three sizes we usually think about with soil. If you have a lot of clay, surprisingly, even though those are tiny particles, they stick to each other really well. And as a result, they don't erode very well or very easily. Sand, on the other hand, is big from a standpoint of erosion, and it's hard to pick up, so it tends not to erode. So most of the sediment that we get from sheet flow, that is just the water flowing straight across the landscape, comes from the detached particles from raindrops. So the sheet flow doesn't actually do much erosion. But again, if we cover up the soil, we don't get the detachment, and we can actually have sheet flow without a lot of erosion. Now, the water moving across the soil tends to congregate. It doesn't stay in sheet flow for very long. And then we get what are called rills. And here's a good picture of rill erosion. So once you get water concentrated like that, it has enough power to erode the soil beyond what the raindrops are doing. So you can see down here at the bottom, you have the rills on the hillside, and then at the bottom you see all the soil that's been eroded off the hillside. And once we got into the flat area, there was not enough energy to move that soil, so it dropped out. So we have both erosion and deposition in this picture. I call this my Friday afternoon slide. So you can see they've stabilized the slope at the far end with grass, and in this case they used hydromulch. We'll talk about different kinds of mulches later. And then on the right, they didn't get around to it, and so they had a rainstorm and look at all the rills. So they're going to have to come back and work that again, reseed it. So this is a good example of once you get to final grade, once you get the slope the way you want it, it's good to get it covered up immediately, because you never know when a big storm is going to come along. Now, when you get beyond rill erosion, you get to gully erosion, and that's what you're looking at here. So top left, that's a really good example of the gullies and how they form. So you see the little cave on the left, that is a gully that is about ready to undercut itself and cave in, which is what's happened on the right side. So you look over here and you'll see all that pile of soil. Well, that caved in. So now the water's going to come along in this waterfall, wash all that out, and start this process all over again, and then it'll cave in. And as a result, you can get a lot of erosion, a lot of sediment moved out. And so you really don't want to ever see gullies like this on a site. This is a mismanagement evidence right here. So down here is a great example. Unfortunately, I find my examples on campus a lot, and this is a construction site that has been neglected for so long that this Grand Canyon has formed. So you really hope never to see that on your construction site. So how many times have I said this? Ground covers reduce soil erosion by stopping which part of soil erosion? Gullies, transport, sedimentation, or detachment. That's really what we're talking about. So what can we do, I guess, to reduce erosion? Well, you can see on the far left of this graph, this is the erosion amount in tons per acre per year. That's how we typically measure it. And so once you get the landscape stabilized, paved and grassed, etc., very low amounts of erosion. But if you're running a farm, depending on how you run it, you may have quite a bit more erosion. But if you look at any of these compared to bare soil, which is what we have on a construction site, they're much lower. So we have a lot of soil erosion happening on construction sites because we have to grade, we have to move the soil, so it's going to be bare. And every time it rains, we're going to have massive amounts of erosion. And again, that's why we're here today, because we want to control that sediment and keep it from getting off the project. And this is a graphic sort of indicating what kind of loads you can get during different phases. So before construction, say you have an open weedy field, and then during construction you have massive amounts of soil being moved around. Then after construction, hopefully you've stabilized it and you don't have very much erosion at all. So part of the reason we worry about all this soil moving around is because we can create all kinds of problems. So here you can see a silt fence, which was not designed to handle this concentrated flow that's coming from this large area. And so all this sediment built up, and finally it's now out on the road. And once it gets on the road, that's a sure way to get phone calls to your local regulatory agencies and notices of violations and other things. So that's something we really want to avoid, is getting mud out on a live road. And here you can see the silt fence has failed here. Yeah, just kidding. That's a landslide. You're not going to be able to control a landslide. So you also can get off-site damage to properties. So here's a farm with a nice pond, and we got sediment moving from a construction project out towards that pond. So that owner over there is not going to be very happy. Here we have another evidence of sediment that's been moving around and getting off-site into a right-of-way. We certainly don't want to ever see lots of sediment getting into storm drain systems. And as you'll see, we spend quite a bit of time talking about how to prevent this from happening. A couple of reasons, but for one thing is these storm drains tend to go straight to a creek. So if that mud's going into the storm drain, then it's going straight into a creek as well. Secondly, you can see over here on the right, if the pipe starts to get filled up with mud, then before you can finish the project, someone's going to have to wash all that out. And that's going to cost a lot of money and take a lot of time. So you want to prevent this from happening in the beginning. So there's lots of things we can do to surround these storm drain systems and keep them from seeing a lot of mud getting into them. And as I mentioned before, we certainly don't want to see any evidence of sediment moving off our project. So if we see this in a wetland, mud getting out into a wetland, or on the right, you can see the silt fence failed and we have mud out in the buffer, and then we have mud all the way into the stream. That's going to get a lot of attention. And typically, in order to come back into compliance, agencies will force you to go out with buckets and pick up all that mud and get it back onto your project. So you can imagine a team in these areas having to shovel all this out, because you can't put equipment into these jurisdictional areas. So it's going to have to be done by hand. So these are things you want to avoid, and that's part of our training, is to make sure that you're paying attention. If you got a big storm coming, make sure everything is buttoned up and you don't have any chance of these types of things happening. So some more examples of problems that can occur if you have sediment moving off your project. This muddy trout stream you see in the upper right, that's not the way trout streams are supposed to look, as most of you know. And in fact, this contractor had to come in with a specialized vacuum system to vacuum all the mud out from between each of these rocks. So you can imagine how much money that cost and how hard it was. But that's habitat for the trout, and they wanted to make sure that they got it back to the way it was supposed to be. And here's a lake. This is real common in North Carolina. You see a lot of lakes with sediment in the upper reaches that has deposited from the creek that maybe feeds that lake. So we want to avoid all that. The sediment's really bad for pretty much everything that is living and trying to live off of the water in streams and lakes, estuaries, etc. If you, this is an old picture. Fortunately, I don't think we're going to see this anymore, but this is before we had good sediment controls that were required. And in this case, this stream is completely filled up with sediment. And when they did a biological assessment in here, they found really nothing living, none of the life that you'd expect to see in a creek. So you don't want to see that, and that's why we have regulations now to force us to keep that sediment on our site. So how can we reduce erosion by 90% or more? Well, hopefully by now we've got this message that just covering up the soil will be a big measure in reducing erosion. Now we're going to talk a little bit about controlling turbidity. Turbidity is a measure of how clear the water is. And in this case, we're seeing turbidity going down. That is getting less clear. The water's getting less clear because of sediment that's coming from construction. So some good examples here. And if you see this is actually a violation. So anytime you increase the turbidity of a stream, we'll talk about the levels, but anytime you do that, then you are actually technically in violation. Now, we don't often enforce that. So lots of times, I know in the lower right, this construction site was completely buttoned down. It had all the practices in place. Everything was working in the way it was supposed to. But that clay that gets suspended is hard to settle. And we'll talk about how you can maybe improve that a little bit. So what are the allowable discharges of turbidity in the state waters? So this table shows you what that is. I'm going to skip forward and show you what those numbers mean. So here's 10. So you can see just barely discolored. And 50, I call that weak T. And 100 and more, it's pretty hard to tell the difference. They're just opaque. You can't really see. So getting back here, so the streams are in North Carolina. You're allowed to discharge up to 50 NTU water. So that's from any site, any industrial process, etc. And lakes and reservoirs, it's 25. So we generally use those for drinking water, so we don't want to have a lot of turbidity in there. And then trout are very sensitive to turbidity, so we're going to keep it to that 10. Now, you see that asterisk at the bottom. If the turbidity in these bodies of water exceed these levels, so the 10, 25, or 50, due to natural background conditions, then the rule is you just can't make that stream or that lake any more turbid than it was. Typically especially in our Piedmont, when we have heavy storms, the streams have turbidities that could be 500, it could be 1,000. So we just can't make those any worse than they are. So again, just calibrate your eye about what turbidity looks like. For drinking water, if you're a supplier of drinking water, let's say for the city of Raleigh, your scale of turbidity is going to be 0 to 0.1. So this would be way too turbid for tap water for most of the water suppliers in North Carolina. So lots of things can happen if you get turbidity into the water. Mostly the impacts are adverse, and we get higher temperatures. The bass can't find their prey if you're a fisher person, and all sorts of negative results when we get turbidity in the streams. So one way we can attack this is by adding a chemical called polyacrylamide. And what that does is it causes the fine particles to stick to each other and become more like sand particles and fall to the bottom. So this is an example here of I guess these are Gatorade bottles, looks like, turbid water, and then it was treated, and you can see what happened. All the turbidity got clumped and settled to the bottom. And so there's a number of ways we can deploy this technique on construction sites to get this turbidity at least reduced. So if you're going to measure turbidity, generally you're going to use a meter that looks like this. You take a vial and get your sample from your stream and put it in the meter and measure how much light can get through it. And that gives you that number of 0 to 1,000 NTUs. There's some ways of managing turbidity. If you're along the shoreline and you're working right by the creek, you may not be able to put any measures in, as you can see here. So instead, you might put in a turbidity curtain. But most of the time, we're not doing that. Instead, we're going to put our polyacrylamide, you see here this powder, we're going to put it on our check dams and maybe some other places, but mostly on the check dams, so that as the water passes through them, the check dams, it picks up some of this chemical and we get that turbidity reduction. In worst case, I don't know, I've seen this on a DOT project. In the worst case, you may have to install a portable water treatment plant, as you see on the lower right. I've seen that on Walmart construction sites, but not very often, very expensive. All right, let's see if we've been paying attention here. If a stream turbidity is 200 NTUs and it's discharging, and I have discharges from my project going into that stream, what number does my discharge have to reach? So it can't exceed 50 NTUs. I just can't increase it. It cannot exceed 200 NTUs, or my discharge is just not allowed at all. But there's actually two correct answers here, essentially. The answer is you can't increase that turbidity. So if the stream's at 200, when you measure turbidity after your discharge point, then it has to be no more than 200. And so actually C is also correct, because if your turbidity was higher than 200 NTUs, then you would increase this most likely. So the key is, though, if your turbidity is over these numbers of 50, 25, or 10, you just can't make that stream go any higher. All right, so any questions then about soil erosion and impacts and turbidity? All right, I can see now from the chat everybody's good. Ted, you want to give it a shot again? Talk about regulations.
Yes, sir. Sure will. Let me pull up that one. Bear with me just a second.